Okay. So far in the course, we basically started with a simple common source, and that we converted to a 5 transistor differential amplifier. And then to boost the gain, we decided to boost the output resistance, and that gave us the cascode configuration. And this itself we could realize either as a normal telescopic cascode or a folded cascode. And in the last class we saw gain boosting as another technique to boost the output resistance of a cascode, and this again you can do it for either telescopic or folded cascode, right? Great. So basically now you guys know how to design a single stage OTA, and you know a bunch of techniques to increase the gain of the OTA, right? So if all were ideal and things were nice, that's it, right? End of the course. You don't have to learn anything more. But unfortunately for you guys, or fortunately for me, that's not the case, right? So we have to deal with whole bunch of stuff, and the most basic thing you'll have to deal with is the following, right? So I mean, let's say you want to measure the gain of this guy. You apply a small sinusoid and you measure how much it gets amplified, and you repeat this experiment by varying the frequency of the sinusoid. So what do you expect will happen to the magnitude of the gain? It kind of, I mean, at least everyone is convinced that it will drop. And why is that so?
Unity gain frequency at some point.
I mean, you don't even know what is unity gain frequency, okay? Yeah, I mean, basically it's just capacitors, right? Essentially the MOSFET, although it looks plain and harmless like this, it has a whole bunch of parasitic capacitors between each of its terminals. So let me just, I'm sure you guys know this: gate to drain, gate to source. So you have something here, and remember a MOSFET has also 4th terminal, substrate, body or bulk, whatever you call it. So you'll always, I mean, you'll also have a capacitor from drain to bulk and from source to bulk, right? So because of all this, if you keep increasing the frequency, the capacitors will start to offer lower impedance, and that, loosely speaking, kills the gain. Fine. So now you no longer can define a gain as a single number. Right? It's no longer a single number A. So how do you characterize it? I mean, I can't define a constant gain. So what do you define? It's a function of frequency, and we define it. We use Laplace transform. Right? A of S, because we like Laplace. Okay. Yeah, and the standard form to write the transfer function is this: A naught into, say, 1 plus S by Z1, S by Z2, dot dot dot. Okay. I'm sure you know this. So what is A naught in this thing? It's a DC gain. That's essentially the gain that you evaluate. Yeah, at DC. That's basically the gain that we have been computing all this time, right? So we have not considered capacitors. It's just the DC gain that we have computed so far. So but now we also have to compute the location of poles and zeros, and as usual we'll start with simple single transistor structures: common source, common gate, common drain. We look at the pole zero locations, and based on the understanding we get from there, we'll try to get a qualitative estimate of poles and zeros in other topologies like 5 transistor OTA, cascode, everything. Fine. And even before going there, I just want to brush up a couple of things about poles and zeros, which you might have already learned in your earlier course, but I'll briefly touch upon so that everyone is on the same page. So starting from poles, so you guys know that the number of poles in a system is equal to the number of independent state variables that can be initialized. I'm sure you have heard this in some form or the other, right? In circuits, state variables basically belong to those elements that can store energy. So what elements can store energy? Yeah. So here we just have capacitor voltages or the inductor currents as the state variables. And in this course we'll most likely ignore inductors, so it's just capacitor voltages. Okay. So the number of poles in our circuits is it's to be actually right, it's the maximum number of independent variables, so it will be more strictly correct. I mean, because if I can set 2, I can also set 1, so it doesn't mean the number of poles is 1, right? It is the maximum number of capacitor voltages I can independently initialize in my circuit. Okay, so I'll write it here. It's the max number of independent capacitor voltages that can be, okay, like this, initialized. And also please recollect that poles is essentially a characteristic of your particular system, and it has no bearing to where you apply the input or where you take the output from, right? So it captures the so-called natural response of the system. So it's not dependent on where you apply the input or where you take the output, right? So I'll write it here. It's independent of input and output. Fine. And okay, let's quickly look at a couple of examples so that you know. We'll start with a simple case, simple RNC, right? And yeah, and see, as I mentioned, since the poles are not going to be dependent on the input or output, for finding if we have poles or estimating the pole locations, we don't have to consider the input. We'll assume that the input is 0. So it's essentially 0. Fine. So here, how many poles we have, or how many state variables I can initialize? One capacitor, I can set its voltage. I can initialize its voltage. Huh?
Why did we short the input?
Because the poles don't depend on the input or output, right? So I can as well look at it without the input,
Yeah.
right? Loosely speaking, you can think of it like this, right? I mean, if this capacitor had an initial voltage, how it's going to discharge over time? That's what the pole captures, right? Okay. So here it's clear, we have one capacitor, I can initialize its voltage, so we have one pole. So if I put one more, how many? Here also I can initialize voltage across this capacitor as well as this. Independently I can set them both, so we have 2. So then this is the next thing. Now if I go and add another capacitor, now what happens? Now also it's still 2, because the moment I set the initial voltage across these 2 capacitors, this voltage is automatically set. Basically I can set only 2 voltages here and the third will get set automatically, right? So although we have 3 capacitors, their voltages are not independent. One is dependent on the other 2. Okay. So in general, let me write, we have 2 poles, and in general if we have these kind of capacitive loops, this might happen wherein not all capacitor voltages will be independent. One might be dependent on the rest of it. So whenever you have such capacitive loops, just be careful. So I'll just say beware of capacitive loops. So this is about finding the number of poles. Now let's see if how we can get a simple estimates on locations. And again, as usual, I'll start with this guy, RNC, R1, C1. So what is the location of the pole here? Yeah, it's 1 by R1, C1. I mean, see, this is a left half plane pole. Okay, ideally I should have minus, but I'm not writing here because the way I have written my transfer function is this. Poles are inherently assumed to be in the left half plane. Okay, so that's why I'm not writing the minus sign. Okay, great. So essentially if we have just a single RC, it's trivial. Pole is equal to the inverse of the time constant, so it's just 1 by C times the resistance it sees. It's very simple. But let's say now I have a cascade of 2 RC sections. Okay, again, I don't have to consider the input, I'll short it now, it's fine. So let us say R1, C1. So here it's actually not trivial to say where the poles are, right? Obviously, if you have two poles, but you can't say it directly. But let us say I do the following. Let's say I go and put a voltage buffer. Now, can you comment anything about the pole locations? Yeah, why? Yeah, I mean, simply speaking, the act of putting this buffer is kind of isolating the two RC sections. This guy is not loading, no longer loading this. Again, if you have to find the transfer function, apply input here, you know the transfer function from here to here is so on, something. And from here to here is product of that. There is no coupling between the two RC sections. So here I can safely say that the location of the poles is 1 by R1 C1, right? So essentially I can treat them as two independent RC sections. So it's first order section, 1 by time constant gives the pole. Okay. So this I'll write it here. If this is a case where the poles are, I would say, decoupled. Now let me get back to the earlier case where we have this. So now based on what we have seen here, can you tell me, is there some condition under which I can approximate the pole location here as 1 by R1 C1 and 1 by R2 C2? R2's? Yeah, looks like, I mean, see, the other way to think of this guy is, the moment I put this buffer here, this is preventing the loading. In other words, the resistance looking here is what? It's infinite, right? So as long as I keep that resistance really large, you can still approximate. Okay. Again, I'll give it as an exercise. You can work out the transfer function and check it for yourself. So here again, it turns out if R2 is greater than R1, you can do it. Okay. And let me also move it to next page. And in addition, it turns out that even if C1 is greater than C2, this still holds good. Again, you can work out, but I'll just qualitatively explain, right? See, let's say you're trying to find the transfer function here by applying input somewhere and measuring the output somewhere. And then you try to find this frequency response. You start at DC. At DC, what can you say about the capacitors? They're open circuited. So when you start from really low frequencies, both capacitors are open, right? And now let us say keep increasing the frequency. And I know for a fact that C1 is much greater than C2, right? So as you keep increasing frequencies, the impedance of the capacitor is going to reduce. Which one do you think will start to reduce first? C1, right? So as I keep increasing frequency, it is the capacitor C1 that will start to not behave like an open circuit, right? Earlier, both of them were acting like good open circuits, but as I keep increasing frequency, it is the capacitor C1 that will start to deviate from its open circuit behavior, right? So the first pole will be contributed by which capacitor do you think? C1. Okay. So the low frequency pole is going to be contributed by this fellow, right? So I'll just write it here. At low frequencies, this capacitor C1 will deviate from open circuit. Okay, but what can you say about C2 at that frequency? It might still behave like an open circuit, right? C1 is really larger than C2. Earlier, both of them were acting like good open circuits. So now we have come to a point where C1 has started to drop, but C2 is still acting like a decent open circuit, right? So I can basically redraw the circuit like this. C1 is active, but C2 is still Open. So now can you tell me, we just have one capacitor. It's a first order RC section. Pole location is trivial. What is the pole location? Sorry, this is C1. This is C1. Yeah. What is it?
1 by R.
So that is a low frequency pole approximately. Fine. Now let's say I keep doing this experiment now. I keep increasing frequencies. I come to a point where C2 has started to deviate from its so-called open circuit behavior. So at that point C2 is going to introduce the second pole, right? But at the frequency where C2 has started to deviate from open circuit behavior, what can you say about C1? It will almost act like a short. So again, at high frequencies, I can approximately say that C1 is like a short. So C1 is like an infinite capacitor. Fine. So now once again I can redraw the circuit. C1 is a short. Just have this. So this resistor is a useless guy. It's not doing anything. So what is the pole location now? That's all. Okay. Right. So basically, to summarize this, whatever you have seen.
If R2 is much more greater than R1, then how we commented about the pole location being on the R1 and C1?
Again, there the logic is looking in resistance is very large.
You should compare looking in impedance, not the resistance.
Yeah, impedance again. Assumption is this guy is, if R2 is really large, right? So the at low frequencies, you might come to a point that this is acting like a lower impedance compared to this. Okay. Right. So again, you can work out in you can work out the transfer function and see it.
Across frequencies, and it will be contributed by both the resistance and the impedance.
Which one?
The impedance we have to
Correct.
calculate across frequencies.
Correct. But the point is, the assumption is this is going to contribute to the low frequency pole. Till that frequency, looking in is really large. I mean, this can be a small impedance. Doesn't matter, right? If R2 is really large, that is going to dominate.
And at low frequencies, the input impedance is very small.
No, input resistance is large. What are you saying?
Input resistance is large.
Uh-huh.
Input impedance.
No, impedance is also same, right? Impedance is series combination of these two, right?
That is very high
Very high.
at low frequency.
Yeah. At high frequencies, it is simply R2, right?
What about the looking left side?
Oh, looking left. Yeah, I mean, that is separate thing, right? We are just, I mean, I went from the buffer case to here, right? The idea was that this guy is kind of isolating these two sections, and it turns out even if this is satisfied, this will happen. But the more, the practical case that we will deal with is this actually. Okay.
Because the buffers ensures the separation decoupling.
That is exactly
of all
correct.
frequencies.
Yeah, that's why that is exactly correct. This is approximation, right? Is this okay? If I have this condition, is this argument okay? So, to summarize what the 2 points I want to make, if we have decoupled poles, I can say that the kth pole is approximately the kth capacitor times the equivalent resistance it sees, and I can do it for each RC section like that if it is decoupled. And for a second order case, we just saw if let us say I have a second order system where this contains only let us say Rs and Gms, I have only let's say two capacitors C1, C2. So if one capacitor is much greater than the other, so that one of the poles is much smaller than the other, so that I'll write in English, I'll say that the poles are far apart. If this happens, we just saw how can you approximate the low frequency pole? I mean, how do you find the low frequency pole?
Consider C2 open.
You'll assume that the other capacitor is open and find what is the effective resistance we see looking here across C1. So that is the low frequency pole. So that is, I'll write as C1 I'll use this notation, we'll not use it later, but for for completeness I'll use, I'll call it R10, where R10 is the resistance seen by C1 when all the other capacitors are open. Here this basically C20. I will not use this notation later, but for completeness I'm introducing this, that's all. Similarly, how do you find the high frequency pole? We'll assume that C1 is now a short. Okay, we'll short C1 and find what is the resistance looking into C2, and 1 by C2 times that gives the pole. So that I'll denote as R21, where 21 says the resistance seen by C2 when C1 is shorted or C1 is infinite. Basically the notation is whatever I write on the superscript, that if I mention 1 or 2 or 3 whatever, that denotes the capacitor that needs to be shorted. That's all. If it's 0, everything is open. You don't have to bother memorizing this, it's just a notation, that's all. Okay. Yeah, and this you can also extend for higher order systems, and let's say we have third order case where C1 is this, and again let us say the 3 poles are this. You can generalize this in a similar way to higher order, but there one more assumption has to be held true. I'll hand wavingly say that. So that assumption is all the resistance are of the similar order. Except let us say R10. Okay. Again, this might look a lot of approximations, but if you think about it, in our amplifiers, let us say we look at the OTA, right? This OTA is going to drive some other circuit or some other load. So that is going to have a load capacitor, and the capacitor will be much smaller than all the parasitics you are going to have inside. So this condition will most likely be satisfied in many cases, and even among the parasitic capacitors, you know that the gate to source capacitance is the maximum, right? So you can always find a case where one capacitor is dominating than the others. So this will hold decently good. And also remember that since the load capacitor is going to be the largest one, so this is like our C1 here, right, the largest capacitor. And if I try to find the output resistance, do you think that's going to be large or small? We want it ideally as large as possible. So this R10, which is the resistance looking here for us, in our amplifiers it's going to be really large. So except R10, if you find all the resistance inside might be of similar order. Again, I'm just giving you this, you'll see it when we come to the circuits. For higher order systems, if turns out under some conditions you can still do the same thing. So to find the low frequency pole, what do you do?
Short all of the capacitors.
No, you're not shorting any. We are looking at low frequencies.
Open all of them.
Yeah, I'll assume C2's both guys are 0, and then find the resistance looking into C1. Okay. For finding P2, what do we do?
Short C1, open C2.
Yeah. Now we have come to a frequency wherein P2 has started to dominate, and at that frequency C1 is already behaving like a short, but C3 is still an open. Okay. And for this guy,
Both previous.
that's all. Both of them are infinity. Okay. Sometimes we might also have a case where we clearly have one capacitor to be much greater than other, but the other two capacitors we might not know. It might be of similar order. So in that case, to find the pole associated with C1, you still do the same thing. It is the largest capacitor. So at low frequencies, that's going to start dominating, but other two capacitors will be like an open. But when you try to find the pole associated with C2, I can only say that C1 is acting like a short. I might not be able to make any comment about C3. So here I'll do same with this also. has gone back. Okay. Fine. Again, remember that this is all under one main assumption that the poles are all far apart, right? So, I mean, it's okay. You can initially make an assumption like this, find the pole locations, and see if they are indeed far apart, right? If that is the case, whatever we have done is okay. So it is.
In that case, then how will you find the pole in case of C2?
Yeah, I mean, you know only C1 is infinity, and then you try to find what happens there.
There are then two steps there.
There you have to find out. That's all, right? Yeah, we'll see.
Generally, far apart means like in what order?
Yeah, again, that depends, right? I mean, let's say 10 times higher or something. Again, this is all. See, the thing with approximations is, if I say it's greater than C2, more it is greater than, I mean, the more C1 is greater than C2, the equalities holds good even better, right? So roughly, let us say for thumb rule 5 or 10 times. Okay.
So this R10 has to be very large.
Typically, it will be large. In our case,
Has to be much greater than all other resistance.
I mean, what I'm saying is usually, except this guy, it's these should be of similar order. And in our case, we'll find this to be of very high because that is the output resistance.
If that becomes low, then the pole that we are assuming to get low frequency moves to high.
Exactly, that can happen. Exactly. Because as you point out, this is the low frequency pole. If this is also really small, then this might not be at such a low frequency. Okay, again, highlighting, this is under the assumption that poles are far apart. Okay, the entire business of saying that the pole is a capacitor times some equivalent resistance holds good only under this condition, right? Simply because, see, with this approach, we can only find real poles, right? But poles can also be complex, right? So you can have a case where pole is at sigma plus j omega. And if you have a pole at this frequency, what might be the other pole?
Sigma minus j omega.
Why? Okay, think about it. I think why that is also should be the case. Okay, anyways, see, if I have something like this, both their magnitudes are same, right? So this is completely not true. So this will give you only real poles wherein the poles are all far apart. Okay, so let's move on. A lot of time is spent. So let's look at some couple of examples maybe. So let's say
Reason behind complex poles.
reason
Complex poles are in the system.
Okay, that's a different question. We'll encounter one such case. We can see that time.
Like looking at the system, we can't tell like we'll have most of the poles will be real. Most of the poles which we are interested in, low frequency poles will be real.
Low frequency pole. I mean, if one pole is much smaller than the other, that has to be real, right? Because real poles, I mean, if you have complex conjugate in real systems, poles occur in complex conjugate pairs, right? So if you say it is complex conjugate, both should be at the same magnitude location, right? Good. So let's look at this case. So let's say R1 C1 same R2 C2. So here I'll assume C2 is the largest capacitor. So then how do I find the low frequency pole? I mean, first of all, what we might be doing? We'll open C1. So we have this. So what is the pole? Okay. So similarly, if I were to find this guy, what do I do to the capacitors first? Which is shorted? C2 is shorted. If I do that, what do I get?
R1 parallel R2 10.
So these two guys are in parallel. So we get sorry, yeah, thanks. Right. So again, this is all assuming that poles are all far apart. Okay. So let me do one more and then we'll spend so much time. Yeah, okay. Okay, let's take this classic case of capacitive loop. So again here let's assume we can have any case. Let us say C1 is the, or let's say C2 is the maximum capacitance, right? We just know C2 is much greater than everything else. That's all we know, right? And what is the low frequency pole? How do you find? Yeah, I'll open, yeah, these two. No, I mean C2 is maximum. To find the low frequency pole, what do I do? Open rest of the capacitors, right? If I open it, what do I get?
R1 plus R2.
Yeah, so it's basically R1 plus R2 times C2. Okay, so let us say, yeah, what about second pole? How do I find?
C1 plus C3.
Yeah, first what will do the capacitors? C2 is short, then what happens?
Then R1 R2 becomes in parallel and C1 C3 becomes
Yeah,
in parallel.
so if I were to draw it, so I'll have something like this. This is short. So C1 and C3 come in parallel, and same is the case with R1 and R2. So this is R1 parallel R2 times. Similarly, you can find what will happen if C3 is the largest capacitor. You can do it, right? Cool. So that's with the poles. Let's move on to zeros. Okay. So once again, zeros, I'm sure you guys know. At zero frequency, what can you say about the transfer function? Huh? I mean, the name says it, right? What should happen to the? It should go to zero. Okay, that's why it's called zero. Huh? Why is it called pole then? Okay, think about it. I will not explain. Roughly correct. We'll see. Yeah, it's okay. I will not explain. You can think about it. See, which means that my output in Laplace domain is 0 even for non-zero input. That's crucial, right? At pole frequency, I'll just say S equal to some zk. This will happen, right? And yeah, so let us say I have V out of S to be equal to some V of S. What is the simplest operation you can do to make this go to 0? Simplest linear operation. Huh? Sorry, I mean, I give you 5 chocolates. If you should have 0 chocolates, what should you do? Yeah, or give it back to me, right? So basically, so what is the conclusion? Yeah, if I add plus minus V of S, to right? I mean, that's the simplest thing, and in fact, that is one way in which zeros occur in the circuits. And important thing is, this depends on the location of the input and output. We'll see with an example shortly, right? And yeah, one way to get 0 here is we have output get, I mean, if we have output obtained as sum of multiple voltages, each with different phase shifts, then they can all add up to give 0, right? So I'll just say sum of voltages with different phase shifts. We can also have a case where we have currents with different phases getting added, and that flows through an impedance at the output to give you 0. Okay, so it's basically sum of voltages or currents with different phases. If you have a scenario like this in your circuit, you will have a 0, right? And simple examples are these. So let us say this is R1, C1, C2. This is V out. So here, do you think we have a case where output voltage is obtained as sum of different voltages? No, because this is the output, it's just one voltage. What about the second case?
Can be like current source C2.
Yeah, here you see that we have 2 currents, and some of those 2 currents flow into the output, whatever you have here, to get the final voltage. And these 2 currents will have different phase shifts because one is through the capacitor, one is through the resistor. So we'll definitely have a 0 here. So let's also look at this case. So here, if this is the output, here do you think the output is obtained as sum of voltages? Yeah, here it is sum of these two, and again it's a capacitor voltage and a resistor voltage. They will have different phase shifts, so this could potentially give rise to a 0 at some complex frequency, right? So this will also have a 0.
So wherever there's a situation where you're adding or subtracting two
Yeah.
quantities with phase shifts, then
Yes, there will definitely be a 0.
Same goes for inductor and capacitor.
Yeah, I mean, doesn't matter, right? Capacitor is giving a phase shift, same with the inductor, right? Again, this analogy is simple, right? I give you 5 chocolates, take back 5 chocolates, it's 0. That's all. So here, let us say in this circuit, I define the output as this. Now, do you think we have 0?
No.
Oh, right? So that clearly says the 0 actually depends on where you take the output as well as where you apply the input. Okay. So next time when someone gives you a circuit and asks if there is a 0, what should be the first question you ask? Yeah, where are the output you are taking and where is the input you are applying? Okay. So this is something to remember. Right. Cool. So this gives a qualitative feel for how zeros get formed in circuits. So but to get a foolproof way to detect the presence of zeros, you can do the following. Again, I'll just give the final result. So let us say you have a transfer function h of s, which is of this form. Let us say I take let's take an example. It's a circuit containing resistors and 3 capacitors C1, C2, C3, and assume it's a third order system, and the transfer function is of the form some h naught into 1 plus b1s. I'll assume we have 1 0 in the circuit, and then we have this. It's a third order system, right? So now do you think the S term in the transfer function is coming because of the resistors in the network or due to the capacitors in the network? Capacitors? Why?
They give rise to the form.
Yeah. Sorry?
State variables.
No, don't. As even simpler. Why?
they have the 1 by s.
I mean, see, impedance of a capacitor, or let us say admittance, is S times C, right? So S doesn't come by itself, right? It always is accompanied by a capacitor or an inductor. So here we have only capacitors. So this S term is going to come only due to capacitors. So I can rewrite this like this. So it's 1 plus S times, I have 3 capacitors. So I can have, let us say, SC1 times, let us say, some RA. Fine. This term I have rewritten like this. Simply because the S term in the numerator must have come from one of these 3 capacitors, right? Similarly, in the denominator also I'll have something similar. The S term here will also have come from one of the capacitors. So I'll say it is SC1 times some, R11, R21. Fine. What about S square term? Yeah, you'll have C1, C2 times something, C2, C3 times something. Just a second. Right. And S cube, it has to be product of 3. That's all, into something. Right. Okay, so that begs a question. Why can't I have C1 square into something? In the S square term, why can't I have something like this? Or can I have actually?
Capacitor won't be in series with itself, right?
This has nothing to do with series, right? I mean, we are doing just by plain logic. We argued that the S term is coming from the capacitors. So S square must come from product of 2 capacitors. So why can't I have self capacitance multiplied by itself?
So how are you arguing that
I mean, it has to be, S term is coming due to the capacitor, right? So it has to be S times C, and if this is S times C, I should have a resistor multiplying it. See, this is a dimensionless quantity. What is the dimension units of this? Its admittance, it is whatever 1 by ohms. So whatever multiplies here must have units of ohms. That's all. I don't know what this R11 is. It is some resistance. That's all. Okay, back to this. Why not? Why or why not? Okay, I mean, just say, see, this we can prove by contradiction. I mean, let us say in this circuit, I make C2 and C3 to go to 0. What will be the order of the circuit? It's a first order. Yeah, but here you see that if I tend C2, C3 to 0, I'll still have S square C1 square term. That's obviously not possible. Simple contradiction, right? And for that matter, you can't have a term which is of the order Ck power m for m greater than 1. You can just prove by extension. Right?
If it were like a 4, okay.
It has to be just C. It can't be the self-capacitance power of something. That's not possible. Right? So let me actually, okay, that's a digression. Let's get back to the topic. Copy everything. Let me write the transfer function here. Okay, so let me just quickly say the result. See, in this transfer function, let us say this is h of s. Let us say I tend C1 to infinity, right? What will happen to h of s? I mean, let's say, not exact value. See, in the numerator, I'll have some term with C1 into something. Denominator, I'll have C1 times something, finally. So, this will be a non-zero term. Is that fine? I mean, limit C1 tends to infinity. In the numerator, only the C1 terms will dominate. Denominator also C1 terms will dominate. C1 in the numerator cancels C1 in denominator. It will be some non-zero number. Right? And in this transfer function, do you have a 0 or not? We have a 0. I mean, it's obvious, right? So if this happens, this happens if the transfer function has zeros. I'll say has a 0. The same is the case you can do for these also, right? Now let us say I don't have a 0 here. Okay, so I've struck the numerator, it's just 1. Now I do the same thing. What will happen to h of s? It will become 0. And in this case, does h of s have 0? Has 0? I mean, it has no zeros. Is this argument okay? So what? First part is fine. In the second example, what I'm saying is, let us say I don't have this, which means h of s does not have a 0. Now if I go and tend, let us say C1 to infinity, then numerator I don't have anything, it's 1 by something. So now based on this, can you suggest me a technique to detect if the circuit has a 0?
So suppose we have a 0, which is not contributed by C, suppose C2.
Okay.
So in that case, the transfer function will go tend towards 0 if you put C to infinity.
Yeah, what I'm saying is you put all capacitors tend to infinity. Right? So the logic is you take all the capacitors in the circuit tend to infinity. If at 1 second. Yeah. Actually, why don't you say what is the logic then?
One instant it should be non-zero. Then we have a 0.
No. Even if it goes to, yeah, correct. Yeah. Fine. Okay. You tend all capacitors to infinity. If for something we have a non-zero transfer function, then we have a 0. Okay. So by extension, can you say what might be the logic for this? This will detect the presence of 1 0. So if I were to extend for, let us say, 2 zeros, what do you think the logic might be? Yeah. You basically tend two capacitors simultaneously to infinity, take two capacitors at a time, tend both of them to infinity at the same time. If the transfer function is non-zero for any of those combinations, you have a zero. I mean, you have two zeros. So I'll just rephrase this and write it here. So the logic is you for Ck tending to infinity, h of s not equal to 0 for some, I'll just say, I think this might be mathematically correct, yeah, which implies we have 1 0. Now for two zeros I'll put Ci Cj to infinity, of course I is not equal to j, and then if we have h of s not equal to 0, again let's look at examples so that it becomes clear. I'll take the same two cases, I can copy them.
The first one you're tending all three capacitors.
No. In first one, okay, that's an experiment where I started with one capacitor to infinity. I can do for other capacitors also is what I'm saying. See, the logic is finally you tend, if you want to detect if the circuit has 1 0, you take one capacitor at a time, tend to infinity. Do it for all the capacitors in the circuit. If for any of them the transfer function is non-zero, then definitely the circuit has 1 0, right? For finding two zeros, you take two capacitors at a time and do it. Okay. It's actually quite easy to understand the logic. Just think about it. I can actually point you to the original paper. This was actually proposed by Professor Hajimiri from Caltech. So I'll point you to the resources. Oopsie. Yeah. So let's look at this case. Yeah. So let's start with the one in the left. So the output is this. So I'll do the same thing. Let us say I start with C1. I tend C1 to infinity. What happens to the output?
0.
But if I tend C2 to infinity, so which means we have 0. Simple. Similarly, if I define this as the output, I just have one capacitor. I tend that to infinity. Whereas if I go and define the bottom portion as the output, I short it, the output is 0, no 0. Okay. This is a foolproof way to understand, to find if the circuit has zeros, and understanding the origin of zeros this way gives you better intuition to see where the zero is actually coming from, right? So yeah, so this is about the presence of zeros or number of zeros. Let's see how we can find the location of zeros, and that's even simpler than finding poles. I'll again, I'll erase this, make some space. So yeah, see, I know that first of all this circuit has a 0, right? And at that 0 frequency, what can you say about V out of S? It has to be 0 at that 0 frequency. Okay, we don't know what that is. So I know for a fact that this guy is 0. So you can apply KCL at, let us say, this node. So what is the current flowing through the capacitor? This is V in of S. Current here is? Yeah, V in of S into SC2. And what is the current flowing here? V in of S by R1. So sum of these two currents must be equal to the current flowing here. What is that current? 0, because output is 0 at that complex frequency. So this is 0. You simplify it, you have V in of S times 1 plus S R1 C2 equal to 0. Of course, obviously I know V in is not 0. So obviously this guy has to be 0. So where is the 0 located now? So you can do the same thing for the other right side also. So I know V out of S, this is V out. V out of S is 0. What is the current here? If I call it V in, this is what? Yeah, V in by R1. So if I this voltage is basically this current flowing into the series impedance of this, right? And I know that V out of S is 0, and that is in turn equal to I of S times
R2 plus 1 by J omega C.
it's all S, right? Okay. Yeah, and what about I of S? What is I of S?
V in over R.
Yeah. So, right, once again I know V in is not 0, so which means the only possibility is the right side term has to be 0. So that directly gives me the pole at so usually anytime you have this kind of series RC networks, that potentially might be a 0, right? Because the output will be sum of two voltages, so that can give rise to a 0. Okay. So I'll stop here, but before next class, please do the following and come. So we'll start with the, now hopefully you have some understanding of how to find poles and zeros. We'll start looking at our simple single transistor stages, but I want you guys to work out this guy. It's a common source with a source resistance Rs. Okay. Basically, it's applying KCL and doing it. Let us say we have PMOS current source as the load, M1, M2. So you can consider all parasitic capacitors here, right? So you will find that you will have a capacitor C1 here. So first of all, just tell this what all parasitic capacitors will contribute to C1? Only CGS of M1. What about C? CGD of M1. What from M2 will come? C is between gate and drain, right? It might come. Let's see where that comes. So for C0, what all will come? We have drain to bulk from this guy, and also drain to source. Usually that's ignorable. Drain to bulk of M1. What else? Drain to bulk of M2 will also come. Let me write it here. What else? Remember that incrementally, what can you say about gate of M2? Short, right? So what about the gate to drain capacitance of M2? CGD of M2. That will also come in parallel. That will also contribute to C0, right? Is there anything else? All right. Hopefully it's fine. That's okay. The point of the course is not for you to do this. This is a pretty trivial thing you can do. We'll lump everything into 3 capacitors here. Okay. So please apply KCL and find out the transfer function. V out by V in. Okay. So, don't use the approximations we did in today's class. We'll do it later and see how it can be applied here. Okay. Just apply KCL. You have only 2 nodes. Node number 1, say it's V1. Node number 2, right? So you can solve it in any ways. You try to write it like this. We have 2 nodes, right? So you'll have 2 equations and 2 unknowns. So you can express it like this as a matrix, and then do whatever you want, right? It's a 2 equations, 2 unknowns. I don't want to spend time solving this in the class because that's not point of the course. You already learnt it in first year BTech. So do this and find out what this is. Okay. And I'll not solve it in the class. I'll take the result from what you derived and then go. So make sure it is correct, because if it is not correct, the rest of the explanation will be wrong. Okay.
We have to consider R0 and
Yeah. Consider R0 for everything. Include R0. Let's not do that yet. If you have some case like GM R0 plus 1, okay, you can ignore it. This you can approximate to GM R0, that's okay. But otherwise, just do it and